Devendra, you should tell me when we can start.
You can start, sir.
Maybe we wait for some time because.
As you wish, so maybe 2 minutes.
So I'll just wait for a minute.
Here some construction is going on in the background and very noisy from outside.
Should we start now, Devendra?
Yes, sir. Yes, sir, start.
Okay. All right. Well, thank you for.
Let me just introduce you, please. Let me introduce you. Just a short introduction. It's a great pleasure to introduce Professor Will Chen, who is currently a member of the Institute for Advanced Study at Princeton. He obtained his PhD from Penn State University in 2016 under the supervision of Winnie Lee. He's particularly interested in, I believe, the interrelationship between algebraic geometry, group theory, and number theory, especially viewed via the prism of monodromy actions of étale fundamental groups. In his PhD work, Professor Chen showed that non-congruent modular curves can be viewed as moduli spaces of elliptic curves with non-abelian level structures. In some recent, very exciting work, he has resolved the conjecture of Bougain, Gambourg, and Sarnak on the Markov equation. I believe this will appear in the Annals of Mathematics. He has also collaborated with Deligne on some work on the arithmetic monodromy actions. Two aspects I cannot resist the temptation to mention. One is that he has some excellent expository notes as well as some codes for computing on his webpage. The other is that he is passionate about photography. If you visit his webpage, we'll be treated to an unbelievable panorama where we can easily lose ourselves. I just lost myself there. It's very beautiful. And Professor Chen will talk today on modular interpretation of non-congruence modular curves. I believe this talk will be accessible to graduate students. So thank you, Professor. Over to Professor Chen now.
All right. Thank you for that extremely kind introduction. And thank you very much for inviting me to speak here. So this is, I was asked to make this talk accessible to grad students. So I'll try to go slowly, and I guess I feel like there are not that many grad students in the audience, but in any case, yeah, feel free to stop me and ask questions. All right. So we have this. So SL2Z, so I feel like we know at this point from many previous talks that SL2Z acts on the upper half plane by fractional Mobius transformations. And for any finite index subgroup, or for any subgroup of the SL2Z, it also acts on the upper half plane. Some particularly interesting subgroups are given by the so-called principal congruent subgroups. These are the kernels of the reduction mod n map from SL2Z to SL2Z mod n. And we say that a subgroup of SL2Z is congruence if it contains the principal congruent subgroup gamma n for some n. Okay, so some examples. So in this talk, actually, we'll say that, in this talk, a modular curve will by definition be the quotient of H mod gamma, where gamma is a finite index subgroup of SL2Z for some gamma finite index inside SL2Z. So not necessarily congruence. And then we'll say it's a congruence modular curve if gamma is a congruent subgroup and a non-congruence if otherwise. Okay, so some examples of these finite index subgroups are gamma 1 of n. These are the matrices in SL2Z, which are congruent to 1 star 0, 1 mod n. And we find that we know sort of classically that H mod gamma n, the modular curve corresponding to gamma n, it has a modular interpretation. It parameterizes isomorphism classes of pairs, where E comma P, where E is an elliptic curve over C, and P has order n. Up to isomorphism. Okay, and similarly, we can take gamma n. So this is the kernel of the reduction mod n map. Another way of saying that is that it's just all the matrices which are congruent to the identity matrix mod n. And in this case, we have H mod gamma n. This parameterizes isomorphism classes of triples, right? Where E is an elliptic curve, and now in this case, PQ form a basis for the n torsion to isomorphism. Okay, and of course, a very special example of this is when you just take this congruent subgroup to be, say, gamma 1, which is just the whole thing, the entirety of SL2Z. In this case, this is the this parameter is just elliptic curves, I guess. Elliptic curves, let's say over C, up to isomorphism. Okay, and in this case, the J invariant gives an isomorphism between H mod SL2Z and the affine line. Okay, so I will, in this talk, so this quotient, the J line, is often can also be written as N11. In this talk, I'll call it, I will change the notation slightly and just call it M1. Okay, so our task is essentially to, so note here, right, these are all congruent subgroups. So our task is to give a similar description of the quotients of the upper half plane by non-congruents, but finite index subgroups of SL2Z. And at this point, it becomes when actually you quickly realize that if you start with a general finite index subgroup of SL2Z, it's actually going to be difficult to come up with a non-congruence, or to come up with a moduli interpretation for the corresponding modular curve. And instead, a better way to do this is to somehow come up with natural moduli spaces, and somehow from the moduli space associate to that moduli space a finite index subgroup of SL2Z. In particular, what we want is we want to come up with certain moduli spaces, let's call it M, together with a map to M11, such that this, so this M11 is just H mod SL2Z, such that this M is given by H mod gamma. And this map is given by the projection, right? So we want to come up with some kind of moduli space, some kind of M with a natural moduli interpretation, such that somehow the map to M11 is given by, in some sense, forgetting the level structure. So M should somehow parameterize pairs E together with some additional finite data. And the map to M11 should correspond to forgetting that finite data. Okay. But from this perspective, like if you have like a general moduli space and with a map to M11, how can you tell that it actually comes from a finite index subgroup of SL2Z, right? So a necessary and sufficient condition for this is actually that the ramification, so that M should be a curve, and that this should be a finite map, and that the ramification above J equals 0 and 1728 have orders 3 and 2 respectively. But this is actually kind of a, this can be a slightly complicated thing to check. I mean, in general, it might be, it's not totally trivial to check the ramification on a map between moduli spaces, at least in terms of the moduli description. So this motivates, for this reason, and for many other reasons also, it becomes natural to consider, instead of the topological quotient, you want to consider the stack quotient. So you can think of the stack quotient. The the point is that the stack, so let's call this will often be called M11 with a curly M. in our talk. In this talk, we'll call it just M1. This stack quotient is basically, well, you start with the upper half plane, and instead of taking the quotient and just viewing this quotient as just a set, as a topological space, you're viewing it as a topological space with some additional data. And in particular, this additional data includes the data of all the stabilizers, of all the points in the quotient. So for example, in the stack quotient, you know that the points j equals 0 and 1728 are different from the other points because they have sort of larger stabilizers, larger SL2Z stabilizers than the other points. Okay, so one feature of the stack is that there's a natural map from the stack to the scheme, from the stack quotient to the normal topological quotient, which you might call coarsification. Coarsification map, and that this map is a homeomorphism. So really, it is just sort of the topological quotient with some additional data. So as a topological space, the stack is the same as the topological quotient. Okay, this is called the moduli stack of elliptic curves. Okay, and the key point here, for us, one reason why this helps us is that, well, whereas the fundamental group of H mod SL2Z as a topological quotient is trivial, right? It's just the affine line. Pi1 of the moduli stack of elliptic curves is almost tautologically, by definition of the stack quotient, it is precisely SL2Z, right? So what this means is that by the Galois correspondence, we have a bijection, we have an equivalence of categories, really, if you define the categories appropriately. But in particular, we have a bijection between the finite index subgroups of SL2Z and finite unramified covers of M1. Okay.
-1?
Sorry?
You don't take the quotient by ±1?
You mean here?
Yeah.
No, I don't take the quotient by plus or minus 1. This is the point of the stack quotient. If you wanted to take the quotient by plus or minus 1, that would kind of correspond to looking at only the topological quotient. But in the stack quotient, it remembers these plus or minus 1 trivial actually.
And it's called the fundamental group of the orbifold in the geometric language.
Yes, that's right. You can also call it the fundamental group of the orbifold. So in this talk, you can think of orbifolds as basically.
But that is PSL2Z.
No, the fundamental group of the orbifold is, well, okay. So I'm not really too familiar with the orbifold language, but my understanding is that the fundamental group of the orbifold should still be SL2Z. But I don't, to be honest, I don't really use the orbifold language, so I'm not sure what is standard in that.
As if it's a Fuchsian group.
It's a what? Oh, Fuchsian group. Yes, yeah.
SL2Z is not a Fuchsian group.
It's not. I thought. Okay, sure. That okay. Yeah, I'm not too clear. I'm not too sure about the orbifold language. Okay, so the key point is here for our purposes is that the fundamental group of M1 is SL2Z, and so to find moduli spaces which come from finite index subgroups of SL2Z, it suffices to find finite unramified covers, right? Finite étale covers of the moduli stack of elliptic curves, right? And ideally, we want to find finite étale covers of the moduli stack of elliptic curves that come with natural moduli interpretations in terms of elliptic curves with some additional structure. Okay, thankfully, these things exist. There are lots of examples of these finite unramified covers given by Hurwitz spaces. So Hurwitz spaces traditionally were moduli spaces of covers of P1, possibly with some amount of branching, right? And in this case, we're going to consider Hurwitz spaces as, we're going to consider moduli spaces of covers of elliptic curves with some fixed fixed invariants. In this case, we're going to fix the monodromy group. We will fix the Galois group, actually. So let G be a finite group. Then we'll call MG. This is the moduli stack or orbifold of branched G covers of elliptic curves, of varying elliptic curves. So we're not fixing an elliptic curve here. Only ramified above the origin. Okay, and for experts here, we'll actually want to consider this as where the morphisms. So in a stack, remember, the stack sort of remembers it's a topological space, but also remembers automorphisms of objects in particular. And so in this case, we want these automorphisms to be considered modulo the center of G. The point is here that the center of G is naturally inside. So if you have any G cover, I'll explain what a G cover is in a moment. The center of G is lies naturally inside the G equivariant automorphisms. If this cover is called pi, then it lies inside the G equivariant automorphism group of pi. So we want to consider all automorphisms or all morphisms as considered modulo the center. Otherwise, if you don't do this, you'll get something else. You'll get another stack. It won't be what I want, basically. I'll explain the difference in a moment. So remember what I mean by a branch G cover. That means that we have some finite surjective map to an elliptic curve, such that if you remove the origin, what you get is what you get is a finite unramified cover, right? So it's only ramified above the origin, in other words. And so in particular, the local picture down inside this punctured elliptic curve, E minus the origin. So if that's X and that's O, actually, let me make this bigger. Then if you, for any loop that say, as long as it doesn't go through the origin, for any loop based at X, so you can look at the fiber above X and it'll be a finite collection of points. In this case, we in fact actually want, so a branch G cover will be the data of pi together with a certain alpha, where alpha is an isomorphism between G and the Galois group of pi. Or let me just write aught pi. Okay. And what this does, what this isomorphism alpha does is it actually defines an action of G on of this abstract group G on the cover, and which in this case will have to act freely and transitively on unramified fibers. And so this fiber will have cardinality equal to the cardinality of G. And for any such point in this fiber, let's consider this point, you can lift this path, or you can lift this loop to some path in the covering space. And if you fix a base point in the fiber, and you consider liftings of various loops, then for every such loop, there's a unique element of G that sends the starting point of the loop to the end point. And this defines for you a monodromy representation, pi1 of E minus O. And in this case, it's surjective to G. And this is essentially well-defined up to conjugation inside G. And this is because there's some ambiguity, because in order to define this representation, you have to pick a point in the fiber. And if you pick different points in the fiber, then you'll get sort of conjugate representations. So this is the monodromy representation associated to the cover. And conversely, Galois theory tells you that given any surjective map from the fundamental group to G, that will correspond, that is precisely the monodromy representation of some connected G cover of E only ramified above the origin. Okay. So
G has to be generated by only two elements.
Yes, exactly. So in this case, in fact, this implies, right, this implies that G is 2 generated. It must be generated by 2 elements in order to have such a surjection, right? So if you considered groups which are not generated by two elements, then you can still define the stack, but it'll be empty. The definition still makes sense, but it'll be empty. Okay, so the first property of these MGs is that, so we have a surjective, we have a natural forgetful map, right? Given any branch G cover of E, so E is an elliptic curve, you can just send it to E, the elliptic curve. You can forget the cover, right? And that defines a forgetful functor, a forgetful map between these moduli spaces. So it defines a forgetful map from the moduli stack of these G covers to the moduli stack of elliptic curves. And the statement, the first property of this is that this is a finite unramified covering. So finite étale covering. Okay, so this is a non-trivial statement, but it's actually quite general. In fact, this generalizes to if you replace the moduli stack of elliptic curves with MGN, the moduli stack of genus G curves with n marked points, and you can still consider, if you replace this with the moduli space of some, certain covers of genus G curves with only n branch points, then that will also be finite and étale. And this is really a statement about deformation theory. You basically want to prove this at the level of different universal deformation rings, and you want to show that every point this map induces an isomorphism of deformation rings at every point. So this is, but we're not going to talk about the proof. We're just going to take this at face value. And what this means for us is that this forgetful map, so we have a forgetful map, right? And what this means for us is that we can basically study this, because this is a finite étale cover, we can study this MG by understanding the monodromy action of the fundamental group of M1 on a geometric fiber or just on a fiber of this map. So let's take a fiber. So let's take a point. So in this case, to be precise, this should be spec C, and a C point of the moduli stack of elliptic curves just corresponds to an elliptic curve over C. And firstly, what is the geometric fiber, or what is the fiber above this of this forgetful map above this point? Well, remember, this forgetful map just sends a cover to the base elliptic curve. And so the fiber above this should be just basically the isomorphism classes of all G covers of this particular elliptic curve, right? And from what I said earlier, because coverings of elliptic curves are determined, in this case, coverings of elliptic curves only branched above the origin are determined by their monodromy representations. If you sort of unravel the definitions, what that means here is that this fiber is just the set of surjections from pi1 of E circ. So here, E circ is by definition the punctured elliptic curve E minus the origin. So this is just the set of epimorphism surjections from pi1 of E circ to G up to conjugation inside G. Right. Okay, so now we know the fiber. Remember, we're trying to understand this using Galois theory. We're trying to understand this stack by understanding the monodromy group the monodromy action of the fundamental group of M1 on this fiber. What is the fundamental group of M1? This we already stated up here, right? This is just SL2Z, but let me think of this slightly differently. Let me express this slightly differently. So pi1 of M1 is sort of at the base. The way I think of it is by Teichmüller theory, in which case the pi1 of M1 is the mapping class group of in this case of E, let me just say of E, okay, of this particular elliptic curve here. So it's the mapping class group of E. This is the group of self homeomorphisms of E as a Riemann surface up to homotopy. And the point is that the mapping class group acts on various invariants of E. So in particular, it acts on the homology, right? And if you view this mapping class group as acting on homology, then this becomes, you can identify this mapping class group, in fact, with the group SL of the homology of E, of the integral homology of E, which is isomorphic to SL2Z. And that's really how you get SL2Z. But the mapping class group also acts on the fundamental group of E. Well, okay, so E is a torus. So the fundamental group is just Z squared. It's actually isomorphic to its homology. And so if you, when you consider this action in the fundamental group, you don't really get anything new. But you can also consider the action of the mapping class group on E minus the origin, right? E is an elliptic curve, so it comes with this specified point, and so you can sort of, by removing this marked point corresponding to the origin, you can have it act on the fundamental group. And in this case, if you view the mapping class group as acting on the fundamental group of E minus an origin minus the origin, then in fact I guess this is I'm not sure if I should say that this is the Baire-Dane-Nielsen theorem. It might go, it might precede that by quite a bit. But in this case, it's also identified with a group of outer automorphisms of the fundamental group of the punctured elliptic curve, where here this plus means that we're actually considering an index to this plus corresponds to orientation preserving, corresponding to the fact that this is SL and not GL. Okay. Okay, so the mapping class, so what you want to think of the fundamental group of the base as really this outer automorphism group of the fundamental group of the punctured elliptic curve. And at this level, we have a very natural action of this outer automorphism group on this set of surjections, right? This action is just by precomposition. You just take any surjection, you precompose with an outer automorphism. That action is well defined because here we're taking everything up to conjugation anyway, right? And the point is that this is precisely the monodromy action. Okay, so at this point, you should also note that pi1 of E circ. So the punctured elliptic curve, deformation retracts onto the join of two circles. And so this is isomorphic to a free group of rank 2. This is free of rank 2. Right. And so this is free of rank 2, and really just having the outer automorphism group of a free group of rank 2 act on the set of surjections from a free group of rank 2 to various finite groups G up to conjugation. Right. And so all of a sudden, this becomes a very computable thing. Right. I mean, this action, the outer automorphism group, it's isomorphic to SL2Z, is a finitely presented group. This is a finite set, and this finite set is basically identified if you pick a basis of this free group. This finite set is just identified with the generating pairs of G up to conjugation. And so this is actually, one charming feature of all this is that this is the geometry of these moduli stacks and G, at least over C or over Q bar, is very computable. And for any fixed value of G, you can just, there's an algorithm that will, in fact, I've written, gap routines that will just spit out basically all the geometric invariants of the connected components of MG. Okay, so, right, so the point is, this forgetful map is finite itself, and so you can understand MG in terms of this monodromy action. Here's precisely what it is. So the Galois correspondence says, it tells you that the out plus pi orbits on this set of surjections. So from now on, I'm just going to call it pi, just for short. Pi will be the fundamental group of this punctured elliptic curve. So surjections of pi to G up to conjugation. This is in bijection with the connected components of MG. Okay, and so remember here, elements in here are basically conjugacy classes of surjections, and any element of here corresponds to a finite branched G cover, which we'll call pi phi. This is a G cover of some elliptic curve only ramified above the origin. Okay, and very precisely how this bijection works is it just sends the orbit of phi to the connected component containing the corresponding cover, so pi phi. And moreover, you can actually specify exactly what this is. This connected component containing it is precisely isomorphic to the stack quotient of the upper half plane modulo gamma phi, where gamma phi is the stabilizer, is the out plus pi stabilizer of phi. Here, by definition, this is a subgroup of out plus of pi, but you can identify it with SL2Z in this way. Essentially, these, if you view this fundamental group as the mapping class group of E, then you have this canonical identification. Well, okay, so I guess it's not canonical. You have to choose a basis. You have to choose a basis. But if you choose a basis for pi, then you can identify out plus of pi with SL2Z. And using such a basis, this becomes a subgroup of SL2Z, and this becomes the natural action. If you choose a good basis, this will become the natural action of SL2Z on the upper half plane. And so what this says, right, is that the connected components of MG, they correspond to on the one hand to these orbits, but on the other hand, from this you can actually determine exactly what modular curve you get. The modular curve that you get is precisely the quotient, the stack quotient of the upper half plane by this stabilizer, by the subgroup of SL2Z corresponding to the stabilizer. Okay. And another point that we should keep in mind is that the in this bijection, essentially, if you go the other way, right, if you take a component inside MG, then going the other way, you'll get the fiber of this component, sorry, F restricted to M, and you look at the fiber. So remember, we have a map now from M to M1. M is a component inside MG, and here is F restricted to M. You'll just get the pre-image, the fiber above E. And so in particular, for example, the degree of the component over M1 is equal to just the size of the orbit. Okay. So to summarize what we have an epimorphism preserving functor from finite groups and surjections. So the category of finite groups where the morphisms are surjections to, sorry, this is not an isomorphism, to the category of finite étale covers of M1. And remember also by Galois theory, this is equivalent to this category of finite sets with out plus pi action. Okay, and this functor just sends G to MG, which is a disjoint union of H mod gamma phis, stack quotient. And if you want honest modular curves, then you just take the associated coarse moduli spaces. Okay. It's not entirely obvious that this should be epimorphism preserving. The fact that it's epimorphism preserving comes down to the fact that whenever you have a surjection, say G1 surjects to G2 of finite groups, then in fact you get a surjection at the level of maps from F2.
Finite étale,
classic.
finite étale covers may be disconnected, right?
Yes, exactly. Possibly disconnected. I mean, yeah. So in this case, these are the connected components in this decomposition. Okay. So let me just give some examples. So, of course, the most basic example is when G is Z mod N squared, Z mod N cross Z mod N, right? In this case, we find that MG, this is just going to be, so from this description here, this is going to be a disjoint union of various copies of H mod gamma phis. Okay, what are the gamma phis? So we know out plus of pi, we basically want to understand the action of out plus of pi on surjections from this free group of rank 2 to, in this case, z mod n squared, up to conjugation, right? But in this case, conjugation doesn't matter because z mod n squared is abelian. So we just have the action of out plus of pi acting on these surjections. On the other hand, again, because z mod n is abelian, this is any such map factors uniquely through z squared. And the action of out plus of pi just factors through an action of the natural action of SL2Z acting on this set, just by precomposition, right? And now from this, at this point, it's just kind of a exercise in the definitions that the only elements of SL2Z that will preserve any given surjection, in fact, or let me put it this way, any element of SL2Z which preserves such a surjection, in fact, it has to descend to an automorphism of z mod n squared, which it has to descend to the identity automorphism of z mod n squared, which is to say that it maps to the identity matrix inside SL2 z mod nz. And so it's precisely the stabilizers of these elements here are precisely the subgroups gamma n. And so in this case, we'll get the stack quotients h mod gamma n, but we'll actually get more than one, right? Because in this case, as the action of SL2Z, it preserves a certain invariant of this. This invariant is essentially given by the determinant. SL2Z sort of preserves the determinant of this map mod n. And so what we'll get sort of z mod n cross many. And for every element of z mod n cross, which basically represents a certain value of the determinant mod n, you'll get a different connected component. Okay. Another natural example is when G is just a cyclic group. In this case, Mg is connected. Again, you can take a similar analysis and you'll find that Mg is connected and it's just given by H1 of n. So we're just trying to compute stabilizers here. Right. Slightly non-trivial example is when you take G to be a dihedral group of order 2k. In this case, Mg is a disjoint union of their phi of k over 2 many copies of H mod gamma, where gamma is gamma 1 of 2. Or, okay, let me write it this way. Gamma is gamma 1 of 2 if k is odd. And otherwise, it's gamma of 2. K is even. Okay, where does this distinction come in? The point is that when k is odd, the abelianization of this dihedral group is z mod 2. And when k is even, the abelianization is z mod 2 cross z mod 2. Right? And you always have a map. Remember, from this, we find that you always have a map from Mg to M of G ab. And what this really says is that this map, when you take G to be the dihedral group, this map induces an isomorphism on connected components. So basically every connected component of M of a dihedral group is precisely it's basically a connected component of M of the abelianization of the dihedral group, which is an abelian group, and in those cases, these gammas will always be congruents in particular. Okay, another example is when. So these are so far our nice infinite families, sort of going. We have abelian, we have metabelian. We're going to now go to something which is non-abelian finite simple. In this case, what we have is that Mg, if G is A5, then we'll find that it's a disjoint union of 3 components, M1 disjoint union with a copy of M1 and M2, and they all map to the moduli stack of elliptic curves. These two have degree 10, this one has degree 18, and these are defined, you can even compute their fields of definition. These are defined over Q adjoined root 5, and this is defined over Q. it's easy to see that this is defined over Q because this is sort of this whole thing is defined over Q, and this has is the unique component. It's the unique geometric component, which has degrees 18 over M1. Okay, and you can check this decomposition just all follows from doing certain group theoretic computations with with the action of the autoautomorphism of pi acting on these surjections. You can tell that these two components defined over Q join zeta 5 essentially because you have some control. It turns out that these two components parameterize A5 covers with ramification index 5. And you know something about how the Galois, how the action of the absolute Galois group, how it acts on covers with a given ramification. Okay.
Do you get H mod gamma 0 n?
Sorry, H1 gamma.
H mod gamma 0 n.
Sorry, what is the question?
Do you get H mod gamma 0 n for some finite group G? This way.
Oh, okay. That's a good question. You don't. Not at least in this construction, but you get H mod gamma n's, and so by sort of taking appropriate quotients, right, you get H mod, or what I mean by that is if you take, if you consider G structures, right, basically Z mod n squared covers up to some notion of equivalence, then that will essentially correspond to a gamma 0 n level structure.
Okay.
So I don't know if you know this. So in general, for any finite, for any subgroup of GL2 Z mod n, if H is a subgroup of GL2 Z mod n, you can talk about H level structures, right?
Mm-hmm.
And when H is the identity, that gives you gamma n level structures. When H is sort of the pre-image of, or I guess when H is the image of gamma 1 of n, these will give you gamma 1 of n level structures. And I mean, essentially, in order to define, okay, I guess I just want to say, once you have Z mod n level structures, you can basically get all the other level structures by taking, you can consider any other kind of level n level structure as a suitable equivalence class of Z mod n level structure, or Z mod n squared level structures.
Okay.
I have another question. What are in the case of A5, what are the genera of these A5 covers of the elliptic curve?
Yeah, that's a great question. These are all genus 0.
Thank you.
Turns out they're all genus 0. So I'll sort of address this question later as well. Okay, so we have this epimorphism preserving functor, right? Finite groups and surjections given any G, you can produce a finite unramified cover of the moduli type of elliptic curves MG. And it's got a very combinatorially defined, very computable geometric description. But this, naturally, it's natural to ask what are the properties of this functor, right? What are the properties of MG? Okay, so here are some specific questions, or more specific questions. Do all non-congruence modular curves appear this way? Right, so originally we were trying to find moduli interpretations for non-congruence modular curves. So have we, in some sense, obtained all of them? And this is essentially answered by a theorem of Asada in 2001, which he showed that every finite index subgroup of SL2Z contains gamma phi for some surjection from pi to some finite group G, right? And so in a similar sense, just as once you know all gamma n level or once you know all Z mod n squared level structures, that basically gives you all congruence level structures by sort of considering suitable equivalence classes of Z mod n squared level structures. In some sense, this tells you that every non-congruous modular curve H mod gamma, well, it's covered by H mod gamma phi, right? And in some sense, you can say that H mod gamma is a moduli space for a certain notion, certain equivalent classes of gamma phi level structures, where these gamma phi level structures have a very natural meaning. They're just in terms of G covers, right, of punctured elliptic curves with a particular topological type. Okay, so basically the answer is yes. And later a theorem of Ellenberg-McReynolds I think in the maybe 2012 or something, they show that if gamma contains the negative of the identity matrix, then H mod gamma appears as a component of mg mod ot g for some g. So it sort of appears on the nose, it's not just covered. Okay, so in some sense, the answer is yes. The answer is yes, we do, all non-congruous modular curves do appear this way. Another natural question is, so this kind of naturally leads to the question for which phi is gamma phi congruous? Right. We've seen already that, okay, so it's pretty easy to show that if G is abelian, then essentially by this kind of consideration, right, by noting that if G is abelian, then this set is really in bijection with this set, and this action is really given by the natural action of SL2Z on Z squared. From this, it's easy to see that when G is abelian, these gamma phi should be congruous. But what about the converse? So on the other hand, we saw here that if G is a dihedral group, right, this is non-abelian, we still find that the components of Mg are congruous, strangely. So in general, it seems to be a difficult thing, whether, this question seems to be remarkably subtle. One thing we can say in a joint work with Deligne, we show that if G has solvable length at most 2, so really the content of this of the following statement is that is in the case of solvable length 2, in other words, metabelian, for example, the dihedral groups, then gamma phi is congruous for all surjections onto G. Okay, and sort of in a slightly different direction, we have that if phi of x, phi of y, so here x and y are generators for pi. So if the images of these things inside the monodromy representation are pairwise co-prime, then gamma phi is non-congruous. In fact, in this case, it's totally non-congruous in the sense that it's the congruence closure. The smallest congruence subgroup containing it is SL2Z. Okay, so these two theorems basically, the point of these two theorems is that it should kind of show you, it should indicate a certain pattern, right? It should indicate that somehow, or a certain philosophy, that if G is very close to being abelian, then these moduli spaces will be, the components of these moduli spaces will be congruence modular curves. And if G is kind of very non-abelian, then they should be non-congruence modular curves. The point being here is that this is kind of a very non-abelian notion, right? In an abelian group, this cannot happen. This sort of breaks as much as possible, right? Whereas in a non-abelian group, for example, A5, you can find a generating pair, X and Y, of orders 2 and 3, such that their product has order 5. Okay, so the idea is that basically if G is very non-abelian, then moduli spaces are congruence.
So you show this by this unbounded denominator?
No, I don't actually. So this thing is just a totally group theoretic argument. You can find it in my thesis paper. Yeah, none of this uses unbounded denominators. I guess in my thesis paper, I sort of deduce some properties of modular forms from these moduli spaces, but I don't say anything about. Yeah, I don't know how to apply that's an interesting question. You know, how can you apply? So now we know the unbounded denominators conjecture is true. How do we apply that? What does that say about the moduli spaces? Well, one problem of really using it to say anything about moduli spaces is you don't even know which moduli spaces are congruent or not, right? Hence this question. And in fact, let me just give you another example to show that this is quite non-trivial. If G is PSU35, this is a very large non-abelian finite simple group. I think its order is like 30,000 or something to that effect. Then MG is a disjoint union. So actually, let me just write it as there are 67 non-congruence components. And you know, I've computed them all, and you can compute their genus and so on. And then there are two copies of H mod gamma, where in this case, gamma it's a level 3 congruent subgroup. And it's normal inside SL2Z of index 3. So there are 67 non-congruence components, and then sort of 2 random congruent subgroups. And in fact, I've been able to identify this as there's a certain construction that you can that comes from the Borel representation by specializing the Borel representation at certain primes. So the Borel representation, these are representations of braid groups. And by specializing that at certain primes, you can get certain characteristic quotients of the free group of rank 2. And the fact that these are so characteristic, finite, simple, non-abelian characteristic quotients of the free group of rank 2. And in fact, you can find that PSU35 is such a quotient. It is in fact a characteristic quotient of pi. And because it's characteristic, that's why it leads to these sorts of these connected components of very low degree over M1. And essentially anything of low degree over M1 has to, sufficiently low degree over M1 has to be congruent, right? Any sort of low index subgroup of SL2Z has to be congruent.
Are these 67 components different, or some of them can be the same?
Some of them can be the same. I mean, they're not all the same. There's a lot of variation, but some of them can be the same, just like in this A5 picture.
Yeah, sure. So do you know how many are same? I mean, like how many are different?
Yeah.
Just curious.
Yeah, I can send you a list.
Oh no, okay. Awesome. All right. Thanks.
Yeah. It's I can even maybe at the end, if you want, I can share screen on my computer and I can sort of show you some of these computations. Okay. Finally, another question, right? Which is, another sort of very vague question is, what is the structure? So what is the geometric structure of MG? Right. So by this, let's say connected components, maybe genus of the connected components, right? So really, the first question is the connected components, right? If you don't know that, if you don't know the connected components, you can say almost nothing about these things, about these modular curves, right? And it turns out this is at this point we're already almost stuck. So when G is abelian, or when it's a meta-abelian, in this case, then you can actually say quite a lot about the connected components. It turns out all the connected components are isomorphic. In the abelian case, that's easy to see. In the meta-abelian case, it's more difficult. They're all isomorphic and they're all congruent, and you can put, you can sort of bound, you can control their congruence level in terms of natural invariance in terms of G. When G is sort of, let's say, so the difficult case is when G is very, very non-abelian, right? And so in this case, there's not even with one exception, there doesn't exist an infinite family of, let's say, almost simple groups for which the connected components even has a conjectural description. The only example of this is when G is SL2P. And there's there are conjectures of McCulloch-Wanderley, and also a special case of which is actually a certain conjecture of Bourgain, Gambard, and Sarnak, which describe the connected components of M of SL2P. So let me just state the theorem in the conjecture. So the theorem is, so let MP be a connected component of M of SL2P modulo GL2P. Okay, so the point is GL2P acts, so remember M of SL2P, right? To understand its structure, you want to look at this set, right? The surjections from pi to SL2P mod conjugation inside SL2P. And now we're gonna sort of further quotient this set out by GL2P. So not just by acting by conjugation as well. So this is basically effectively quotienting out by an order 2 subgroup, or an order 2 group. And so what we get is going to be a degree 2 quotient of M of SL2P. Okay, so let this be the component classifying, or sorry, be the substack. This is an open and closed substack classifying covers with monodromy trace is equal to -2. What do I mean by monodromy trace? Remember, these are covers of elliptic curves only ramified above the origin, right? And these are in this case SL2P covers of elliptic curves only ramified above the origin. If you take a small loop around the origin, a small loop around the puncture essentially in the elliptic curve, and you lift it to the cover, that will, depending on the choice of lifting, that will determine a conjugacy class of SL2P, and you can take its trace. So by monodromy trace, I mean the trace of the monodromy determined by a small loop around the puncture, around the origin. So this is a discrete invariant. And so this determines the substack of this, which contains all SL2P covers. There is an open and closed substack with this prescribed monodromy trace. So the first statement is that MP is connected for large P. Okay. The second statement is that the genus of MP, so you can find, once you know it's connected, again, connectedness is the hardest part. Once you know that it's connected, you can compute the genus without too much difficulty. And in fact, in this case, you can come up with a very explicit formula for the genus. And one consequence of that formula is that the genus is around 1/12 P squared. And you can even say that the error term is like O of P to the 3/2. Okay, and the last point is that the monodromy of this connected component over M1, the monodromy group, is alternating or symmetric. And again, you can sort of determine when it's alternating or when it's symmetric depending on P, some congruence condition on P. And this is, so to be precise, this is only true for this is only known for a density 1 set of primes. Okay, so this is work of Bourgain, Gambard, Sarnak, and myself. This is, I guess, just once we know connectedness, this is sort of this B is kind of a computation, and C is work of Mary Puder, assuming connectedness as well. Okay, again, the connectedness part is the hardest. So I only have 1 minute left. So maybe I will just describe in words how this works. So the connected part is the hardest. This connectedness part, right? If you from this Galois correspondence, what you're really showing, what you want to show is that a certain transitivity of the action of out plus pi acting on some set of surjections. And the point is that in this case, we want to understand the action of out plus of pi acting on the surjections from pi to SL2P, in this case, mod GL2P. But we want to consider the subset of this because of this condition, monodromy trace equals -2. We want to consider the subset such that the trace, so the condition monodromy trace equals -2 translates group theoretically to the trace of the image of the commutator. So if pi is generated by A and B, then we want the trace of the image of the commutator to be -2. Okay. And again, we get an action of out plus of pi on this set. So the action of out plus on this set preserves this subset. And we want to show that that's transitive. And the point is that this set is in bijection with a set of FP points, except for the origin of a certain cubic surface. So basically, this cubic surface appears inside the character variety of SL2 representations of pi, where pi is a free group of rank 2. And it turns out in this particular case, you have this very nice description for the rational points of this character variety. It's in fact defined by precisely this equivalence condition on the set of actual surjections, abstract group theoretic surjections. And this we have an action of out plus of pi. This action on this translates to an action on the FP points. And the work of Bourgain, Gambert, and Sarnak, they showed that this action, by analyzing, in fact, you can write down coordinates for the action, right? Out plus of pi is generated by 2 unipotent elements. You can actually write down exactly what those unipotent elements, how they act on this surface, on this affine surface. And they analyzed this action very, very explicitly. They really showed that essentially one key point is that if you specialize x, y, or z, one of the coordinates to some fixed value, then what you get is a conic. And it turns out that these unipotent elements preserve the restrictions, right? They preserve the specializations of, okay, let me rephrase. They preserve the conics that are obtained as specializations of the coordinates. And on these conics, they act by essentially rotations, hyperbolic rotations, or I guess parabolic like translations. And what Bourgain, Gambert, Sarnak do is that they have a very, they really get their hands dirty, and they really try to like connect points to other points using these rotations. And it's a lot of sort of very, it's a lot of, there are a lot of very difficult estimates. And what they're able to show in the end is that there is always a large orbit whose complement is has size subpolynomial in P. And what I show is that essentially that the size every orbit has size congruent to 0 mod P. Right? In particular, every orbit has size which is at least polynomial in P. And so that implies that in fact there is for a large P, for all but finitely many P, there's only one orbit. And this fact comes from a certain algebraic algebraic geometry, and it comes from using sort of basically it comes from studying these stacks, and in particular it comes from studying the universal families over these stacks. Okay, so I'm a little over time. I'll stop there. Thank you.
Oh, thank you for this really wonderfully clear talk. Actually, so there should be questions, I guess. So any questions? Professor Kulkarni?
Thanks for a nice talk. Actually, I just have a quick question. Maybe you already said it. What's the significance of monodromy trace -2? I didn't understand that.
Right. So I didn't say it, and that's a good question. The significance of it is that I can't prove anything without Bourgain, Gambert, and Sarnak's work. I mean, I can always prove this type of statement. Okay. I guess. Okay. Another point is, okay. So I guess there are multiple reasons. Firstly, why did Bourgain, Gambert, and Sarnak just do monodromy trace 2? Well, they were interested more in this originally in this particular surface. This is called
the Markov. I see. That's the.
And this corresponds to monodromy trace -2. In general, what you find is that this, if this surface corresponds to monodromy trace K, right? And they sort of were initially interested in the Markov surface, though they can still say things about other surfaces, but they, at least their exposition, their write-up really only considers a Markov surface. another point of view is that their statement that there's a large orbit whose complement has size which is subpolynomial in P, right? That statement doesn't depend on the monodromy trace. On the other hand, my statement that every orbit has size converted to 0 mod P, this P does depend on the monodromy trace. And it corresponds to the fact that the only elements of SL2Z, or sorry, SL2P, which have order dividing P, are the unipotent things, right? Basically 1, 1, 0, 1, sorry, I guess it's plus or minus 1, and then something, right? And then plus or minus 1 here. And so monodromy trace, so it turns out trace 2 doesn't appear. And so trace -2 basically corresponds to the only allowable things of element of order P. And why do you get, where does the P come from here? Well, this P actually comes from the ramification index of the covers that you consider. And right, so in general, I'll get some congruence modulo something which depends on the ramification index. And only for the trace -2 case does that actually give you, congruence mod P. In general, it won't give you something which is, in general, it won't give you something which is, say, polynomial in P.
Thanks.
Some other questions?
What are the references?
The references, okay. So on my website, there's a paper, there's an archive preprint currently. And I've also posted a bunch of talks I've given on this particular problem. I guess those are the references.
Okay, thank you. Any other questions?
Sorry, a question. Why you didn't consider infinite index subgroups of SL2Z? Just work with finite index subgroups.
Yeah, so that's a good question. One reason is that I like algebraic geometry, and when you consider infinite index subgroups of SL2Z, the quotients aren't really Riemann surfaces anymore. They're not algebraic curves.
Thanks.
Right.
So you don't consider thin groups and so on, right?
Yeah, I don't consider thin groups. Right. And especially in fact, any questions about moduli spaces, I don't even know. I feel like these questions are often asked in the language of algebraic geometry. I'm not really used to thinking about moduli spaces from another language.
Just wondering about you have solvable length 2. What about the P groups or something? Is there anything you can say which is
yeah, that's a great question. So I mean, that's definitely a very interesting thing to consider. One thing I can say is, okay, so this theorem of Asada, right, says that for every finite index subgroup of SL2Z contains gamma phi for some phi, right? And in particular, every non-congruence modular curve, congruence or not, is covered by a component of mg for some g. So one could ask, what is a family of finite groups G? Right, I mean, it would have to be infinite. Can you find an infinite family of finite groups G such that you get this, such that every modular curve is a quotient of a component of mg for some G in this family? Okay. One thing I can say is that P groups are not enough.
I see.
This follows from, there's a paper, I don't know if you've heard of this, there's a paper of Matsumoto and Tamagawa, where they compare mapping class group actions on fundamental groups, on pro-P fundamental groups of curves to the Galois actions. And it follows from a result in there.
Interesting. Thank you. So any other questions are there? Otherwise, let's thank the speaker. Thank you very much. It was a pleasure listening to you.
Nice talk. Thanks.
You're welcome. Thanks.
Over to you, Devendra.
Sorry for chairing also this session. And thanks, Will. Maybe
You're welcome. Thank you. Thank you for inviting me.
Okay.
Is there any connection to the unbounded denominators?
Yeah, right. So one connection is it turns out that, okay, if you have a component M inside MG, okay, so you can, so remember every component of MG, right, is basically the stack quotient of H mod some gamma, right? And you can ask, so suppose gamma is non-congruous, and you can ask whether or not it has unbounded denominators, whether or not modular forms for gamma have unbounded denominators. One thing you can say is that, well, it turns out that these stacks, these have good reduction. Or let me put it this way. The important thing is that this map, the forgetful map, is finite étale away from the primes dividing G. So this stack also, above I only talked about these stacks over C because that was the simplest. But all this map makes sense. And these stacks certainly make sense over Z adjoint 1 over the order of G, and this is still étale. And wherever it's étale, it turns out that you can show that in this case, this étaleness implies that all modular forms for gamma phi have bounded denominators at primes not dividing the order of G. So this is actually some result which is not known by the work. It does not follow from the work of Caligari, Tang, Dimitrov, and Tang. It does. So they show that they prove the unbounded denominators conjecture, but they don't show that if from their work it could still be the case that you have unbounded denominators, but like you have unbounded denominators at infinitely many primes, right? That's possible. Like maybe the denominators sort of get more and more divisible by more and more primes, by unbounded collection of primes. And this actually shows that that's not the case. That can't happen. Yeah. So this is explained sort of from the final section of my thesis paper on moduli interpretations for non-congruous modular curves. Fleshes out this argument. It's not super complicated.
Thank you.
Sure.
So any other questions also? Welcome. Okay, thank you so much then. Thank you again. And see you then.
Welcome.
Bye.
Bye-bye.
Bye.